Reality is far more complex and baffling than our everyday experiences suggest. The world we perceive, the solid ground beneath us, the steady flow of time, the clear cause and effect relationships, forms a fragile illusion, a carefully constructed facade that begins to crumble once we delve beneath the surface. At the quantum level, the world becomes a realm of paradox and uncertainty, a domain where atoms seem to flicker in and out of existence, and particles can be in multiple places simultaneously. Here, the act of observation itself plays a strange role, altering the very reality it seeks to measure. For many centuries, humanity embraced the idea of a universe governed by order, predictability, and fixed laws. Newtonian physics, and later Einstein's refinements, provided a framework that appeared to explain everything with remarkable accuracy. It was a cosmos where objects moved in predictable orbits, where cause led to effect in a clear chain, and where the clockwork universe ticked along with precision. Yet, as physicists began probing the smallest scales of matter, they uncovered a far stranger reality beneath that reassuring surface. The atoms, once thought to behave like miniature planets orbiting a nucleus in neat paths, revealed themselves to be anything but stable or definite. At the heart of quantum mechanics lies a concept so alien to everyday experience that it challenges the very way we think about the physical world. Unlike the classical notion of particles as tiny, solid objects moving along definite paths with exact positions and momenta, quantum particles such as electrons occupy a state of ambiguity and fluidity. They exist not as pinpoint dots in space, but as diffuse clouds of probability that spread out across regions where their presence might be detected. This uncertainty is not due to a limitation in measurement technology or incomplete knowledge, but is a fundamental aspect of reality itself. The classical picture, inherited from centuries of Newtonian physics, envisions particles as entities with well-defined properties at all times. If you throw a ball, you can calculate its trajectory precisely, predicting where it will be in the next moment. This intuitive view, deeply rooted in human experience, breaks down completely when applied to the microscopic world of atoms and subatomic particles. Here, the rules of engagement are different. Electrons, protons, and other quantum entities do not have definite positions or speeds until they are actively measured or observed. Before this act of observation, these particles exist in a state described by a mathematical object known as the wave function, which encodes the probabilities of finding the particle in various locations or states. This wave function is not a physical wave like ripples on a pond, but an abstract representation of possibilities. It fluctuates and evolves according to the Schrödinger equation, a fundamental equation of quantum mechanics that governs how the probabilities change over time. Within this framework, the electron behaves as if it were smeared across space, existing simultaneously in multiple potential locations. This superposition of states defies everyday logic and raises deep questions about the nature of existence itself. Is the electron truly everywhere at once, or is it simply that we lack a precise description until measurement occurs? The resolution to this mystery is found in the process of measurement, a concept both essential and perplexing in quantum theory. When a measurement is performed, say detecting the position of an electron, the wave function collapses, and the electron suddenly appears in a definite location. This collapse is not a physical snapping of something tangible, but a radical shift from a spectrum of probabilities to a single actuality. Before measurement, the electron's position was described by a spread-out probability cloud. After measurement, it is pinned down to a specific point. This shift from uncertainty to certainty is instantaneous and, intriguingly, depends on the interaction between the quantum system and the measuring apparatus. This phenomenon, known as the collapse of the wave function, reveals that reality at the quantum scale is fundamentally probabilistic and not predetermined. Unlike classical objects whose paths can be predicted with near certainty, given enough information, quantum particles only reveal their precise properties upon interaction with the environment or an observer. Until then, their states are best understood as a range of possibilities existing simultaneously. This undermines the classical assumption of a fixed objective reality independent of observation and suggests that observation plays an active role in bringing about the specific outcomes we experience. The implications of this are profound and stretch far beyond physics. The idea that the act of observation shapes reality calls into question the distinction between the observer and the observed, the subject and the object. It suggests a universe that is participatory in nature, where consciousness or measurement is not merely passive, but integral to the unfolding of events. Some interpretations of quantum mechanics even speculate that consciousness itself could be connected to this collapse process, although this remains a topic of intense debate and speculation. Furthermore, the wave function collapse is a unique event that distinguishes the quantum world from our classical experience. The concept of superposition, particles existing in multiple states at once, vanishes the moment a measurement is made. Yet the underlying question remains: what precisely constitutes a measurement? Does it require a conscious observer, or can any interaction with the environment cause this collapse? These questions have given rise to numerous interpretations and philosophical discussions, reflecting the unsettled nature of quantum foundations. The probabilistic essence of quantum mechanics also introduces the idea that reality itself is not a rigid deterministic system, but a fluid and open-ended process. The universe at its most fundamental level is a landscape of potentialities where outcomes are not set in stone but unfold probabilistically. This is a radical departure from the classical worldview, where the future is fully determined by the past. Quantum indeterminacy means that certain events cannot be predicted with absolute certainty, only with a likelihood expressed as probabilities. This inherent uncertainty permeates the very fabric of existence and influences phenomena from the behavior of fundamental particles to the processes governing chemistry and biology. Adding to the intrigue, the nature of quantum states and wave function collapse implies a deeper connection between entities that transcends classical spatial separations. Particles in entangled states share a linked wave function, such that the measurement of one particle instantaneously affects the state of the other, regardless of the distance between them. This non-locality suggests that the universe is more interconnected than classical physics allows, with information and influence flowing in ways that challenge our notions of space and time. The idea that reality only becomes definite when observed has also raised questions about the role of the observer. In everyday life, we consider observation to be a passive process, simply witnessing what is already there. However, in the quantum domain, observation becomes a creative act that helps bring the physical world into being as we know it. This participatory quality of reality blurs the line between physical processes and conscious experience, leading some thinkers to propose that consciousness and reality are fundamentally intertwined. Despite the strangeness of wave function collapse, it has practical consequences that are essential to the functioning of the quantum world. It explains how particles behave in experiments like the famous double-slit experiment, where electrons fired at a barrier with two slits create an interference pattern typical of waves. When not observed, the electrons appear to pass through both slits simultaneously, interfering with themselves. But when a measurement is made to determine which slit the electron passes through, the interference pattern disappears and the electron behaves like a particle with a definite path. This duality between wave-like and particle-like behavior is a direct manifestation of the collapse phenomenon and illustrates the fundamental role of observation in shaping physical outcomes. The collapse of the wave function also brings with it conceptual puzzles, such as the apparent randomness of measurement outcomes. While the probabilities predicted by quantum mechanics are incredibly accurate, the precise result of any single measurement cannot be foretold. This intrinsic randomness forces us to abandon the idea of a universe governed by strict causality at the smallest scales. Instead, we accept a reality where chance plays a fundamental role, where the universe constantly navigates among multiple possibilities before settling into specific outcomes through interaction or observation. The quantum world reveals a universe that is not composed of solid, well-defined objects, but rather a realm of probabilities, potentialities, and intrinsic uncertainties. Particles do not have fixed positions or states until the moment of measurement, where the wave function collapses and crystallizes one outcome from countless possibilities. This challenges the classical notion of a predetermined objective reality and suggests a participatory universe where observation is integral to the existence of physical phenomena. It is a realm where certainty emerges only through interaction, where the boundaries between the observer and the observed blur, and where the fabric of reality itself is a delicate interplay of possibility and actuality. This profound insight continues to inspire both scientific exploration and philosophical reflection, reshaping our understanding of what it means to exist in a fundamentally quantum universe. This counterintuitive behavior shakes the foundations of logic and intuition. Particles can behave like waves, and waves can manifest particle-like properties, blurring the lines between what is real and what is potential. The simple act of looking changes the thing being looked at, as if the universe hesitates until we force it to decide what it truly is. This leads to profound questions. If atoms, the building blocks of matter, only become real when observed, what does that say about the nature of the physical world? Is the solidity we experience a projection crafted by our perception? Are we co-creators of reality simply by the act of witnessing it? Adding to the mystery, some particles display a bizarre interconnectedness called quantum entanglement. These particles become linked so profoundly that the state of one instantly influences the other, regardless of the distance separating them, even if they are light years apart. Albert Einstein famously referred to this as spooky action at a distance, skeptical of how information could travel faster than light, yet countless experiments have confirmed its reality. This entanglement defies the usual constraints of space and time, challenging our understanding of the universe's fundamental structure. Furthermore, quantum superposition allows particles to exist in multiple states or places simultaneously. A single atom can follow two distinct paths at once. An electron's spin can simultaneously be up and down. Only upon measurement do these multiple possibilities collapse into one definite reality. This suggests that at the quantum level, reality is fluid and undefined until acted upon by observation. Even the concept of time becomes uncertain in the quantum world. Unlike the fixed, linear progression we experience, time at this scale might not flow strictly forward. Some interpretations propose that the present can influence the past, and the future may retroactively alter events, blurring cause and effect into a more flexible relationship. This challenges the very essence of how we understand the universe to operate. How can the fundamental fabric of existence be so contradictory and baffling? Quantum mechanics is not merely a set of abstract equations, but a window into a reality that defies human logic and intuition. It forces us to question the very nature of existence itself. What truly is real? Is the world we live in a solid, objective place, or is it shaped by our perception and consciousness? If we ourselves are made of these ghostly quantum elements, subject to the same strange rules, what implications does that have for the nature of consciousness and being? These are not just philosophical musings, they are urgent scientific challenges that remain unresolved after more than a century of study. Some scientists argue that quantum mechanics is incomplete, and that beneath its strange behaviors lies a deeper, hidden reality yet to be uncovered. Others accept the bizarre quantum world as it is, where reality is probabilistic and observation-dependent. A more radical group posits that consciousness itself is intertwined with the universe's fabric, that our awareness may actively participate in shaping reality rather than being a passive observer. This exploration takes us into the most perplexing corners of modern physics, a world where atoms seem ephemeral, where particles communicate instantly over vast distances, and where reality blurs between existence and non-existence. We will examine the paradoxes that quantum mechanics presents, the groundbreaking experiments that challenge our worldview, and the profound questions about time, space, and consciousness that science has yet to answer. For centuries, humanity held a firm belief that the universe functioned much like an immense, precise machine. This conception emerged most clearly with the advent of Newtonian physics, which portrayed the cosmos as a grand clockwork mechanism operating with unwavering exactness. According to this worldview, every motion, every interaction, and every event followed fixed, deterministic laws. If one possessed sufficient information about the state of the universe at any given moment, such as the positions, velocities, and forces acting upon every object, one could, in theory, predict all future occurrences with absolute certainty, and also reconstruct the past with equal accuracy. This idea, known as determinism, was deeply comforting because it implied that the universe was orderly, predictable, and governed by unchanging principles. Isaac Newton's groundbreaking work laid the foundation for this vision. His laws of motion and universal gravitation offered a framework so precise that it allowed astronomers to predict the movements of celestial bodies with extraordinary accuracy. For example, the orbits of planets around the Sun could be calculated to the minute, and the tides, the trajectory of projectiles, and the behavior of falling objects all became explainable within this framework. The elegance and simplicity of Newton's laws fostered the idea that the universe was essentially a giant clock, with all parts interconnected and moving in perfect harmony, driven by immutable laws that left no room for randomness or chance. This mechanistic universe was a worldview that not only dominated physics, but also influenced philosophy and theology. The universe's predictability implied a kind of cosmic orderliness, which some interpreted as evidence of a rational creator who set the machinery in motion and ensured its flawless operation. The image of a clockmaker god was pervasive, a divine craftsman who, having wound the clock, allowed it to run on its own without interference. This mechanistic interpretation placed humanity in a universe where everything followed logical, predictable pathways, reinforcing ideas of causality and the belief that natural phenomena were understandable through reason and observation. The implications of this model extended beyond science. It shaped how people understood free will, morality, and even the nature of life itself. If the universe was deterministic, it raised questions about human agency. Were people truly free to choose their actions, or were all decisions merely outcomes of prior causes, unfolding like the gears of the cosmic machine? Philosophers debated these questions intensely, with some embracing the deterministic model as supporting a universe governed by necessity, while others sought ways to reconcile human freedom with this rigid framework. For the scientists of the time, this worldview was immensely productive. It provided a reliable toolkit for exploring the physical world and enabled remarkable technological progress. The ability to predict natural phenomena allowed for the development of machines, navigation, engineering, and many other fields that shaped the modern world. The laws of Newtonian physics became the standard against which all other theories were measured, forming a foundation that endured for centuries. Yet as the years passed, certain phenomena began to challenge this neat picture. While Newtonian mechanics excelled at describing the motion of everyday objects and celestial bodies, it struggled with the very small, the world of atoms and subatomic particles, and the very fast particles moving close to the speed of light. Experiments and observations in these domains revealed inconsistencies that the classical clockwork universe could not account for. At the dawn of the 20th century, the development of quantum mechanics and relativity fundamentally altered the scientific landscape. These new theories exposed the limitations of the Newtonian framework, showing that at the microscopic scale, particles behaved in ways that defied deterministic predictability. Instead of fixed positions and velocities, particles existed in probabilistic states, with outcomes that could only be described in terms of likelihoods rather than certainties. This probabilistic nature was a stark departure from the classical idea of a clockwork universe running with perfect precision. Moreover, relativity introduced the concept that time and space were not absolute but relative and intertwined, depending on the observer's frame of reference. This shattered the notion of universal, uniform time that ticked identically everywhere, a key assumption of the classical mechanistic model. The universe was revealed to be far more dynamic and complex, with properties that varied depending on scale and perspective. Despite these upheavals, the old mechanistic view remained deeply ingrained in both scientific thinking and popular imagination for much of the 20th century. The appeal of a universe governed by clear, deterministic laws was hard to relinquish. It took decades for the scientific community to fully accept that at its most fundamental level, nature was governed by probabilities, uncertainty, and interconnectedness that defied classical explanation. The legacy of the Newtonian model, however, is profound. It demonstrated the power of observation, experimentation, and mathematical description in revealing the workings of the natural world. It ushered in an era where human beings could understand and manipulate their environment in unprecedented ways. Even though the clockwork universe has been replaced by more nuanced models, its influence remains embedded in the way science is practiced and conceptualized. The mechanistic worldview also set the stage for ongoing philosophical and scientific debates about the nature of reality. Questions about determinism, free will, causality, and the limits of human knowledge continue to engage thinkers today. The transition from a predictable, mechanical cosmos to one that embraces uncertainty and complexity invites us to reconsider our place in the universe and the nature of existence itself. In sum, the centuries-long belief in a universe as a vast, predictable machine reflected humanity's quest for order and understanding. It offered a framework that explained much of the natural world and provided a sense of certainty and control. While modern physics has revealed the universe to be more mysterious and less deterministic than once thought, the Newtonian legacy remains a cornerstone of scientific progress, reminding us of the enduring human desire to unravel the mysteries of the cosmos. Yet as scientists delved deeper into the nature of matter, cracks appeared in this orderly facade. The tiny particles once envisioned as miniature solar systems proved far more elusive and complex. Instead of orbiting predictably, electrons and other quantum particles behaved like ephemeral ghosts, occupying multiple states and places simultaneously, defying the classical laws that had long defined reality. This transformation in understanding began with light itself. Historically seen as a simple phenomenon of illumination, light posed a profound mystery in the 19th century. Was it a wave or a particle? Waves and particles are fundamentally different, with waves spreading and interfering like ripples on water, while particles are discrete, localized objects. Early experiments showed light behaving like a wave, bending around obstacles and creating interference patterns. This seemed to settle the debate. However, Albert Einstein's work in 1905 challenged this notion by demonstrating that light also behaves like a particle. He showed that when light hits certain metals, it ejects electrons in discrete packets or photons, much like tiny bullets striking a surface. Thus, light exhibited both wave-like and particle-like properties, a duality that defied classical logic. This discovery shattered the traditional view and marked the beginning of quantum physics, a new way to understand the fundamental workings of reality, where things can be both one thing and another simultaneously. The world at its deepest level is stranger and more mysterious than anyone ever imagined. Quantum mechanics reveals a universe that is not fixed and certain, but fluid and uncertain, shaped in part by observation itself. These insights invite us to reconsider everything we thought we knew about reality, existence, and our place within the cosmos. Experiment after experiment confirmed a bewildering truth. Light behaves both like a wave and like a particle, depending on how we observe it. This dual nature shattered the long-held beliefs of classical physics, revealing that the universe's rules were far more flexible and mysterious than previously thought. Yet, the puzzling behavior of light was only the opening act of a much greater upheaval in our understanding of reality. At the beginning of the 20th century, scientists confronted another paradox that threatened to collapse classical physics entirely. While studying how objects emit heat radiation, they noticed something perplexing. When objects were heated, they emitted light in specific patterns. A piece of iron glowing red at lower temperatures would shift to white as it became hotter. Classical physics predicted that this pattern should continue indefinitely, with hotter objects releasing ever-increasing amounts of high-energy ultraviolet light. However, experimental results contradicted this expectation. Beyond a certain point, ultraviolet light emissions dropped sharply, defying the classical predictions. This baffling failure became known as the ultraviolet catastrophe, a problem so severe it seemed to threaten the entire theoretical foundation of physics. The resolution came from a surprising source, Max Planck. Rather than dismissing the data, Planck introduced an ingenious mathematical adjustment, proposing that energy was not emitted in a smooth, continuous flow, but rather in discrete packets or quanta. These energy quanta restricted how radiation could be emitted, neatly explaining the ultraviolet catastrophe. While initially a mathematical fix, Planck's idea would revolutionize physics by suggesting that energy is fundamentally quantized. This revelation implied a profound change in how we understand the universe. No longer could we view reality as a seamless, continuous machine. Instead, it appeared grainy and granular, made up of indivisible packets of energy that refused to behave in smooth, predictable ways. The classical view of a clockwork cosmos gave way to a universe that was inherently uncertain, probabilistic, and ruled by strange, invisible laws. If energy came in discrete packets, then it was natural to ask, could matter itself be quantized? Soon, scientists turned their attention to the electron, the fundamental particle of electricity and matter. In 1924, a young physicist named Louis de Broglie proposed a bold and unsettling hypothesis. If light could behave as both a wave and a particle, then perhaps electrons could too. This idea was met with skepticism. Electrons were traditionally seen as solid particles with mass and charge, orbiting the atomic nucleus like tiny planets. How could these tangible bits of matter possibly exhibit wave-like behavior? Yet experiments spoke louder than intuition. Researchers found that electrons, like light, could produce interference patterns, signatures of wave behavior. When a single electron was fired through a narrow slit, it didn't behave like a tiny bullet hitting a specific point. Instead, it spread out like a ghostly wave, seemingly traveling through multiple paths simultaneously and interfering with itself. It was only when an observation was made that the electron's probability wave collapsed, localizing the electron in a definite spot. This discovery was deeply unsettling. It implied that electrons lacked definite positions or paths until measured, existing instead in a state called superposition, where multiple possibilities coexist simultaneously. The very act of observation forced reality to choose a single outcome. This was no mere limitation of human perception, but a fundamental truth embedded in the fabric of the universe. Classical physics, with its comfortable certainties and solid particles, was no longer sufficient to describe the quantum world. The more scientists delved into atomic structure, the stranger the discoveries became. Classical physics, once the foundation of our understanding, seemed inadequate to describe the true nature of reality. It was as if a hidden layer beneath everyday experience had been exposed, one where the usual concepts of time, space, and cause and effect unraveled. This shift in perspective was epitomized in 1926, when Austrian physicist Erwin Schrödinger developed an equation that became central to quantum mechanics. Unlike Newton's equations that precisely calculated the paths of objects, Schrödinger's equation described a cloud of probabilities. Instead of pinpointing where an electron was, it indicated where it might be found. Electrons no longer behaved like solid particles with fixed positions, but as spread out waves of potentiality, each location carrying a certain likelihood. This probabilistic view of reality marked a profound departure from classical ideas. An object once thought to be located in one specific place could now exist in many places at once, its exact position undefined until measurement. Schrödinger himself was troubled by the paradox this created, famously illustrating it through his thought experiment known as Schrödinger's cat. Imagine a cat locked in a sealed box with a vial of poison that could be released if a single radioactive atom decays. Because the atom exists in a superposition of decayed and undecayed states, the cat's fate becomes linked to this quantum uncertainty. Until the box is opened and observed, the cat is paradoxically both alive and dead, existing in a liminal state between life and death. Only upon observation does reality collapse to reveal a definite outcome. The cat paradox reveals the deep philosophical quandaries at the heart of quantum mechanics. Does reality exist independently before it is observed, or is it shaped by the act of observation itself? If a single atom can exist in multiple states simultaneously, then is the entire universe only fully formed when measured? This questions the very nature of existence and challenges our assumptions about an objective reality. Many physicists found these ideas difficult to accept. Albert Einstein, in particular, was famously skeptical, rejecting the idea that the universe was governed by random chance and probability rather than strict causality and determinism. He believed there must be some deeper underlying order, a hidden reality that quantum mechanics only partially revealed. These unsettling discoveries force us to rethink what we mean by reality. The classical world of solid, predictable objects gives way to a universe built on waves, probabilities, and the essential role of the observer. Matter itself becomes something ghostly, uncertain, and dependent on measurement to assume definite form. This redefinition of the fundamental nature of existence remains one of the most profound and ongoing challenges in physics and philosophy, shaping our understanding of everything from the smallest particles to the cosmos itself. Einstein famously argued against the randomness at the heart of quantum mechanics, declaring, "God does not play dice with the universe." He was convinced that quantum theory was incomplete, that beneath the strange probabilities there must be a deeper hidden reality where everything unfolded with certainty and predictability. Yet despite his resistance, decades of rigorous experiments have repeatedly validated the unsettling conclusion. Probability is not just a mathematical tool or a placeholder for ignorance, but a fundamental feature of the universe itself. One of the most remarkable and deeply puzzling revelations of modern physics is the discovery that, at the quantum level, particles such as electrons do not have fixed, definite characteristics until they are measured or observed. This is a sharp departure from classical thinking, where objects are believed to have inherent properties regardless of whether anyone looks at them. In the everyday world of our experience, this idea feels strange and even counterintuitive. We assume that a chair remains a chair, a table remains a table, whether or not anyone is watching. But when scientists began probing the behavior of the tiniest constituents of matter, they found a radically different reality, one that challenges the very foundations of how we understand existence. This phenomenon is often referred to as the observer effect in quantum mechanics, though the term can be somewhat misleading. It doesn't mean that consciousness or human observation magically changes the particle. Instead, it reveals that the act of measurement itself, any interaction that forces a particle to reveal a specific outcome, collapses the range of possibilities into one definite state. Before measurement, a particle is described by a mathematical entity called a wave function, which encompasses all the possible states the particle could be in. This wave function is spread out, representing probabilities rather than certainties. It's only when a measurement is made that the particle chooses a particular state, a process that has baffled scientists and philosophers alike. The classic demonstration of this strange behavior is the famous double-slit experiment. Imagine firing electrons at a barrier that has two parallel slits. Behind the barrier, there is a screen that can detect where each electron lands. If electrons were simply tiny billiard balls, one would expect them to pass through either one slit or the other, creating two distinct bands on the detector corresponding to each slit. However, when the experiment is performed, something unexpected happens. Instead of two bands, an interference pattern emerges, a series of bright and dark fringes characteristic of wave behavior. This interference pattern suggests that each electron acts not just as a particle, but also as a wave, passing through both slits at once and interfering with itself. It's as if the electron explores multiple paths simultaneously, something that defies classical intuition. This wave-like behavior continues until a measurement is introduced to determine which slit the electron passes through. When such a measurement is made, the interference pattern disappears and the electron behaves like a particle going through a single slit. The simple act of trying to observe the particle's path fundamentally changes its behavior. This experiment shattered the idea that particles have a fixed, determinate existence independent of observation. Instead, it points to a universe where reality is probabilistic and dependent on interactions. This has deep philosophical implications because it suggests that at a fundamental level, the universe does not have definite properties until those properties are forced into existence by observation or interaction. This counterintuitive behavior is at the heart of quantum mechanics and illustrates the limits of classical concepts such as position, momentum, and trajectory when applied to the microscopic world. It shows that these properties are not intrinsic features of particles but rather emerge only upon measurement. Prior to measurement, particles exist in a superposition, a blend of multiple possible states, coexisting simultaneously. The implications of this discovery go beyond the double-slit experiment. It challenges the notion of objective reality as something independent and fixed. Instead, the quantum world is described by probabilities and potentialities only becoming concrete when observed. This raises profound questions about what it means to observe, the role of the observer, and how reality itself is constructed. Scientists and philosophers have debated for decades over the meaning of these findings. Some interpretations suggest that consciousness plays a role in collapsing the wave function, implying a deep connection between the mind and the fabric of reality. Others argue that measurement is a physical process involving interaction between systems and does not require conscious observation. Alternative interpretations propose that every possible outcome occurs in separate, branching realities, sidestepping the need for collapse altogether. Despite these different views, the fundamental takeaway remains that particles do not carry definite properties prior to measurement, a notion that contrasts starkly with everyday experience. This shift in understanding forced scientists to develop new mathematical tools and conceptual frameworks to accurately describe and predict the behavior of quantum systems. Moreover, the observer effect has practical consequences. It sets fundamental limits on what can be known about quantum systems, as captured by Heisenberg's uncertainty principle, which states that certain pairs of properties, like position and momentum, cannot be simultaneously measured with arbitrary precision. This inherent uncertainty is not due to experimental shortcomings, but reflects a fundamental aspect of nature. The double-slit experiment and the observer effect together provide a striking demonstration of one of the most enigmatic features of quantum mechanics, the wave-particle duality of matter. This duality reveals that particles, traditionally thought of as discrete, localized entities, can also exhibit wave-like properties, behaving in ways that defy classical intuition. It is a phenomenon that blurs the line between what we commonly perceive as particles and waves, suggesting that these categories are not as mutually exclusive as once believed. In the famous double-slit experiment, a beam of particles such as electrons or photons is directed at a barrier with two narrow openings, or slits. If one imagines particles as tiny billiard balls, one would expect them to pass through one slit or the other, creating two distinct bands on a detector behind the slits. However, when the experiment is performed without measuring which slit each particle passes through, a different outcome emerges. Instead of two bands, an interference pattern forms on the detector, a series of alternating bright and dark fringes characteristic of waves interacting and overlapping. This pattern indicates that each particle acts as a wave that travels through both slits simultaneously, interfering with itself much like ripples on a pond. This wave-like behavior is astonishing because it suggests that particles do not have a single well-defined path, but rather exist in a superposition of multiple paths. Each particle seems to explore all possible routes, and the probability of where it will be detected is influenced by constructive and destructive interference between these paths. The outcome, the interference pattern, is a macroscopic signature of this underlying quantum behavior. What further complicates this picture is the role of measurement or observation. When an attempt is made to determine which slit the particle passes through, by placing detectors at the slits or otherwise interacting with the particle, the interference pattern disappears, replaced by two distinct bands corresponding to the two slits. The particle then behaves like a classical particle with a definite trajectory. This shift is the essence of the observer effect. The very act of measurement affects the system in such a way that it alters the outcome. This experimental outcome underscores that the properties exhibited by quantum objects depend fundamentally on how they are observed. It is not that particles simply have dual characteristics hidden within them. Rather, their behavior changes in response to the experimental setup, challenging the idea of an objective reality independent of measurement. The wave-particle duality is thus a dynamic interplay between the quantum system and the measurement apparatus, a concept foreign to classical physics. While electrons are the most commonly discussed particles in this context, wave-particle duality extends far beyond them. Photons, the quantum particles of light, also display this dual nature. In experiments such as the photoelectric effect or single-photon interference, light reveals both wave-like interference and particle-like discrete interactions with matter. This duality in photons laid foundational groundwork for quantum theory and earned Einstein his Nobel Prize. Even larger entities than electrons and photons exhibit wave-particle duality under carefully controlled conditions. Atoms and small molecules, which are far more massive and complex than elementary particles, have been shown to produce interference patterns in sophisticated experiments. Such findings expand the boundary of quantum behavior into the realm of matter that we more readily associate with classical physics. For example, experiments with fullerene molecules, spherical carbon structures composed of 60 atoms, have demonstrated interference effects, proving that wave-like behavior is a universal feature of matter. These results suggest that quantum mechanics is not limited to an esoteric microscopic world, but underpins the behavior of all matter, regardless of size. The ability of larger molecules to exhibit wave-particle duality depends on maintaining delicate quantum coherence, a fragile state easily disrupted by interactions with the environment. This sensitivity to disturbance explains why everyday objects do not visibly exhibit wave-like behavior, and why classical mechanics remains a reliable approximation at macroscopic scales. Wave-particle duality fundamentally reshapes our understanding of reality by dissolving the classical dichotomy between particles and waves. It forces us to view matter and energy as entities that do not fit neatly into either category, but instead possess a hybrid nature. This hybrid character has profound implications for how we model and comprehend physical systems, requiring new mathematical frameworks such as wave functions and probability amplitudes to describe their behavior accurately. The concept also prompts deeper philosophical questions about the nature of existence and observation. If the behavior of quantum objects depends on measurement, then the act of observing becomes more than passive witnessing. It is an active participant in shaping reality. This has led to interpretations of quantum mechanics that emphasize the role of consciousness, information, or interaction in defining what we perceive as real. Moreover, wave-particle duality has driven technological innovations that underpin much of modern physics and technology. Quantum tunneling, superposition, and interference phenomena exploited in devices like electron microscopes, lasers, and quantum computers all hinge on the principles revealed by this dual nature of matter. Understanding and harnessing this duality opens doors to advancements that were unimaginable under classical physics. The double-slit experiment and observer effect highlight a central transformative insight of quantum mechanics, that matter and energy exist in a state that transcends classical categories, displaying both wave-like and particle-like characteristics. This duality is universal, applying not only to fundamental particles like electrons and photons, but also to complex molecules under the right conditions. It challenges our traditional concepts of reality, intertwining observation and existence in a way that continues to inspire scientific discovery and philosophical inquiry. At a broader level, these discoveries hint at a universe far more interconnected and mysterious than previously imagined. They suggest that reality is not a fixed backdrop, but a dynamic interplay of possibilities that become concrete only through interaction. This insight continues to influence not only physics, but also fields such as information theory, computing, and even philosophy, as it challenges assumptions about knowledge, existence, and causality. The realization that particles lack definite properties until observed profoundly transforms our understanding of reality. It reveals a universe governed not by rigid certainty, but by probabilistic potential, where observation plays a crucial role in shaping what is real. This discovery stands as one of the most significant scientific revelations, opening doors to new ways of thinking about nature, knowledge, and the cosmos itself. However, this bizarre wave-like behavior changes drastically when a measuring device is introduced to determine which slit the electron passes through. The moment measurement occurs, the interference pattern disappears. Electrons behave like discrete particles, going through one slit or the other as if they were never waves at all. It's as if the universe knows it is being observed, and reality collapses from a spectrum of possibilities into a single concrete outcome. This experiment, known as the double-slit experiment, is one of the most famous demonstrations of quantum strangeness, showing that the act of observation fundamentally alters reality itself. This raises profound and unsettling questions. What exactly constitutes an observer? Does it require human consciousness, or can any interaction with a measuring device suffice? And if consciousness is necessary, does that mean the universe requires an observer to exist at all? These questions remain deeply controversial and unresolved. Some physicists argue that observation is simply a physical interaction causing the collapse of a particle's wave function, requiring no conscious awareness. Others entertain the more radical notion that consciousness is intricately connected to the fabric of reality, that the mind and universe are entwined in ways we have yet to fully grasp. If consciousness truly influences reality, then what does this imply about existence itself? Could it be that the universe is not a fixed, objective reality, but something shaped and brought into being by conscious observers? And what happens in the absence of observation? Does the universe exist independently, or does it hang in a state of quantum uncertainty? Another extraordinary and puzzling aspect of quantum mechanics is entanglement, a phenomenon Albert Einstein famously derided as spooky action at a distance. When two particles become entangled, they form a linked system so that the state of one instantaneously determines the state of the other, no matter how far apart they are in space. This connection transcends vast distances, seemingly communicating faster than the speed of light and violating Einstein's own theory of relativity. For decades, Einstein suspected there must be hidden variables, unknown elements that would explain this connection without breaking the rules of causality and locality. Yet, time and again, experiments have verified entanglement as a genuine physical phenomenon. Measurements on one particle instantaneously influence the state of its entangled partner, even if separated by light years. This raises profound implications for our understanding of space and time. Perhaps at the quantum level, the concept of space loses its traditional meaning. Could there be invisible threads weaving the universe into an interconnected whole, transcending the limitations of distance and time? Does entanglement hint at a deeper layer of reality, an underlying fabric that classical physics cannot touch? As physicists have ventured further into quantum theory, the more the mysteries deepen. The atoms once imagined as solid, indivisible building blocks have transformed into ethereal apparitions, clouds of probabilities flickering in and out of existence. The idea that reality is fixed, objective, and independent has given way to a world that is fluid, uncertain, and dependent on measurement or observation. The comforting certainty of Newtonian mechanics has vanished, replaced by a cosmos where probabilities reign, where particles can be in multiple states simultaneously, and where mere observation changes the nature of what exists. The universe, it seems, is not a perfectly predictable machine, but something far stranger and more enigmatic. Quantum mechanics is not a niche theory applicable only to atoms and electrons. It underpins the entire foundation of reality itself. The more scientists peer into the quantum world, the more unsettling and profound the questions become. What is the nature of existence when certainty dissolves into probability? How can space and time hold meaning in a reality where instantaneous connections defy classical limits? Is consciousness merely an observer or an active participant in shaping the cosmos? These questions are far from settled. They challenge not only our scientific models but also our fundamental understanding of what it means to exist. Quantum mechanics forces us to reconsider reality itself, hinting at a universe that is far more mysterious, interconnected, and alive than we ever imagined. It is a realm where the boundaries between the observer and the observed blur, where the fabric of space and time becomes malleable, and where the deepest truths of existence remain tantalizingly out of reach, waiting for us to uncover and understand. If particles can exist in two places at once, then the idea of entire universes coexisting simultaneously becomes a serious possibility. If time and causality, our intuitive understanding that the past causes the future, are actually illusions, then could events in the future influence what has already happened? And if the universe needs an observer to exist, then what or who observed the very first moment of time, the birth of everything? These questions shake the foundations of everything humanity has believed about existence, and they signal that the journey into the bizarre realm of quantum mechanics has only just begun. The collapse of classical physics was not merely a scientific correction, it was a total upheaval of the principles that humanity had depended upon for centuries. For a long time, reality was thought to be a stable, clockwork machine where cause led to effect with perfect reliability, and the future was predictable from the present. But the advent of quantum mechanics revealed a universe far more elusive, a vast web of probabilities, overlapping states, and paradoxes. With every new experiment, the universe appeared stranger, less deterministic, and more unsettling than anyone had imagined. One of the most profound shifts involved time itself. For millennia, time was viewed as a constant, moving inexorably forward. The past created the present, which then shaped the future, a straightforward linear procession. Even Einstein's theory of relativity, with its insights about time stretching or contracting depending on speed and gravity, still maintained a forward progression of time. Quantum mechanics shattered this certainty. At the smallest scales, time seemed to lose its conventional meaning. Particles didn't flow through time the way objects in the everyday world do. Instead, past, present, and future appeared to coexist or influence one another simultaneously. Certain interpretations of quantum mechanics suggest that a particle's future state could affect its past behavior, a total reversal of traditional cause and effect. This is illustrated by the delayed choice experiment, a fascinating twist on the classic double-slit experiment. Usually, particles behave like waves when they pass through two slits, creating interference patterns unless an observer measures which slit the particle passes through. Then, the particle acts like a single defined particle. But in the delayed choice setup, the decision to measure the particle is made after it has already passed through the slits. Remarkably, experiments show the particle seems to know in advance that it will be measured and retroactively adjusts its behavior to match that outcome. This challenges everything we think we understand about time. How can the future alter the past? How can a present decision reach backward and influence something that has already happened? These findings suggest quantum systems do not obey the linear time rules familiar to us. Instead, past and future might be deeply intertwined aspects of a larger, interconnected reality. Such puzzling results have led some physicists to a radical conclusion. Perhaps time itself is an illusion. Unlike space or energy, time does not appear as a fundamental ingredient of quantum reality. Some theories propose that time emerges only at larger scales, where many quantum events collectively create the sensation of time flowing forward. At the quantum level, reality might exist in a timeless state where past, present, and future are simply different perspectives of the same whole. If this is correct, our experience of time passing may be a kind of illusion generated by the way our brains process information. Instead of the universe changing moment to moment, all moments could already exist simultaneously, with consciousness moving through them, much like a needle playing a record. But if time is an illusion, then what does that mean for reality itself? Are we living in just one slice of a much broader, timeless existence? The many worlds interpretation of quantum mechanics is one of the most fascinating and mind-expanding ideas in modern physics. Proposed by physicist Hugh Everett III in the 1950s, this interpretation offers a radical solution to the long-standing problem of how the quantum world connects to the reality we observe. At its core, it suggests that the strange behavior of particles in quantum experiments, like the double-slit experiment and the mysterious collapse of the wave function, can be explained if we accept that every possible outcome of a quantum event actually happens, but not in a single universe. Instead, reality splits or branches into multiple parallel universes, each containing a different outcome. To appreciate why this idea is so revolutionary, it helps to first understand the dilemma it addresses. In quantum mechanics, particles exist in a superposition of states. This means that before measurement, an electron, for example, is not simply in one place or another, but exists in a combination of all possible positions simultaneously. However, when we measure the electron, we see only one outcome. It appears in a specific place. The traditional or Copenhagen interpretation of quantum mechanics says that the wave function collapses when observed, forcing a particle to choose one definite state out of the many possibilities. But this collapse process is mysterious and raises many questions. Why and how does it happen? What counts as an observer? Is the act of measurement fundamentally special? Hugh Everett proposed a bold alternative. There is no collapse. Instead, the universe itself splits into multiple branches at every quantum event. Each branch corresponds to one of the possible outcomes, all equally real but separate. This means that for every quantum decision, the universe fans out, creating a vast multiverse of parallel realities where every possibility is played out. The wave function never collapses. It simply evolves deterministically according to the Schrödinger equation, which governs quantum systems. Imagine an electron passing through the double slit. According to many worlds, the universe splits into at least two branches. In one, the electron goes through the left slit, and in another, it goes through the right slit. Each branch has its own version of the detector screen registering the particle's impact. We, as observers, find ourselves in one branch or the other, experiencing one outcome, but both outcomes exist simultaneously, just in separate, non-interacting universes. This interpretation leads to profound implications about the nature of reality and our place within it. If every quantum event branches reality into countless new worlds, then there is an unimaginably vast multiverse, where every possible history and future exists. In one universe, you might have taken a different path in life. In another, you might have made different choices that changed everything. Somewhere in this infinite web of realities, there is a universe where historical events unfolded differently, where dinosaurs never went extinct, or where entire physical laws diverge from what we know. This multiverse is not just a philosophical curiosity, but arises naturally from the mathematics of quantum mechanics when the collapse postulate is removed. It elegantly sidesteps the thorny issues associated with wave function collapse. Since no special role is assigned to observation, the theory restores a deterministic evolution to the quantum state, removing the need for randomness or magic at the moment of measurement. However, this beauty comes with its own conceptual challenges. One of the most unsettling questions is what happens to you when the universe splits. According to many worlds, each quantum branching creates copies of observers, versions of yourself who exist simultaneously but in separate realities. These copies share your memories up to the point of branching, but then diverge as events unfold differently in each universe. This raises deep questions about identity and consciousness. Are these parallel selves genuinely you, or are they separate individuals sharing a common origin? The idea that countless versions of ourselves live out every possible decision can be both thrilling and disorienting. Moreover, while the many worlds interpretation resolves some quantum puzzles, it remains controversial and is difficult to test experimentally. By its nature, the different branches do not interact or influence one another once they split, making it challenging to obtain direct evidence of their existence. Some physicists accept many worlds as a plausible or even inevitable consequence of quantum theory, while others favor interpretations that do not multiply universes. Despite this, the many worlds interpretation has found resonance not only among physicists, but also in popular culture and philosophy. It offers a vision of reality where possibility is endless, and every choice and chance outcome is realized somewhere. It reframes our understanding of chance and fate. There is no random collapse or final outcome, only a sprawling cosmos where all outcomes happen. This idea also influences how we think about probability in quantum mechanics. Instead of probabilities reflecting the likelihood that an outcome will occur, they are interpreted as measures of how much weight or presence each branch has in the multiverse. Some branches may be more probable or common than others, but all exist. This shift from a single, definite reality to a constantly branching multiverse challenges centuries of philosophical assumptions about existence and causality. Furthermore, the concept of parallel universes in many worlds aligns with certain developments in cosmology and theories of the universe's origins, such as eternal inflation. This framework imagines a cosmos constantly creating bubbles of space-time that evolve independently, somewhat like the branching quantum realities, but on a cosmic scale. In this way, the many worlds interpretation connects quantum phenomena to the grand structure of the cosmos. At first glance, the idea seems pulled straight from the pages of speculative fiction, yet within theoretical physics, it is treated with surprising seriousness. The many worlds interpretation emerged not as a whimsical fantasy, but as a rigorous attempt to confront some of the deepest inconsistencies in quantum theory. At its core, it proposes a radical solution to a long-standing mystery. Instead of asking why one outcome becomes real while others vanish, it suggests that nothing ever disappears. Every possible result of a quantum event continues to exist, each unfolding in its own distinct version of reality. In conventional interpretations of quantum mechanics, the wave function describes all the possible states a system can occupy. When a measurement is made, This wave function is said to collapse, leaving behind a single definite outcome. However, this collapse has always been problematic. The mathematical equations governing quantum systems do not actually include a collapse mechanism. It is introduced as an extra assumption. The many worlds interpretation removes this assumption entirely. According to this view, the wave function never collapses. Instead, it continues to evolve smoothly, branching whenever a quantum event has multiple possible outcomes. Each branch represents a fully realized world in which one specific outcome occurs. If a particle can be measured in two possible states, the universe divides into two branches, each containing a version of reality consistent with one outcome. Importantly, these branches do not interact with one another after they form. From the perspective of an observer inside any given branch, it appears as though a single outcome occurred and all other possibilities vanished, even though they persist elsewhere. This idea elegantly sidesteps the question of why observation seems to play such a powerful role in quantum mechanics. There is no special moment where reality chooses. There is no privileged observer collapsing possibilities into facts. Everything that can happen does happen, governed purely by the deterministic equations of quantum theory. Ironically, this interpretation restores determinism at the most fundamental level, even though it multiplies realities to do so. Yet this solution comes at a heavy conceptual cost. If every possible outcome exists, then reality becomes unimaginably vast. Every decision, every random event, every quantum fluctuation produces new branches. In one branch, a choice is made, in another it is not. In one, a life unfolds in a familiar way, in another, it diverges sharply. The result is a continually expanding multiverse composed of countless parallel histories. This raises an immediate and deeply unsettling question about identity. If there are infinite versions of you, all originating from the same past but diverging over time, what does it mean to be you? Traditional notions of self are grounded in continuity, a single body, a single stream of experience, a single life story. The many worlds interpretation fractures that continuity. Every time a branching event occurs, multiple successors emerge, each with equal claim to being the continuation of the person who existed before. From an external theoretical perspective, none of these versions is more authentic than the others. They all arise from the same physical laws and share the same history up to the point of divergence. Yet subjectively, each version experiences itself as unique and singular. Each feels like the only one, unaware of the countless others unfolding elsewhere. This disconnect between objective multiplicity and subjective singularity lies at the heart of the philosophical tension. Why then do you experience this specific sequence of events rather than another equally valid one? The many worlds interpretation offers no special mechanism to explain this. It simply states that every version of you experiences its own branch from the inside. There is no cosmic selector choosing which perspective you inhabit. From within the theory, the question itself may be misplaced because there is no single you to choose from. There are only many continuations, each equally real. This challenges deeply held intuitions about free will and personal responsibility. If every possible choice is realized somewhere, does choice actually matter? Some argue that it still does because each version of you must live with the consequences within their own branch. Others find this unsatisfying, feeling that the existence of alternate outcomes undermines the meaningfulness of decision-making. The debate touches on age-old philosophical questions about determinism, agency, and moral accountability. Probability also takes on a strange new character in this framework. In everyday life, probability reflects uncertainty about what will happen. In the many worlds view, uncertainty is subjective rather than objective. All outcomes occur, but an observer does not know in advance which branch they will experience. Probability becomes a measure of expectation rather than chance, tied to the relative weight of different branches rather than the likelihood of an outcome occurring at all. Critics often point to the sheer extravagance of the idea. postulating an enormous, ever-branching multiverse seems excessive, especially since these parallel worlds are, by definition, unobservable. Supporters counter that the interpretation does not add new physical laws or entities beyond what quantum mechanics already implies. It simply takes the mathematics at face value without inserting an ad hoc collapse to preserve classical intuitions. Despite decades of discussion, there is currently no experimental way to distinguish the many worlds interpretation from other interpretations of quantum mechanics. All make the same predictions for observable phenomena. As a result, the debate remains largely philosophical, hinging on which conceptual framework one finds most coherent or least troubling. Some physicists favor many worlds for its mathematical purity, while others reject it for its metaphysical implications. What makes the interpretation especially provocative is how directly it confronts our sense of uniqueness. Human experience feels singular and irreplaceable, yet many worlds suggest that this feeling may be a feature of perspective rather than a reflection of reality's structure. Each branch contains conscious beings who feel just as real, just as central as you do here. There is no privileged storyline, no cosmic main character. Ultimately, the many worlds interpretation forces a re-evaluation of what it means to exist at all. Identity becomes less about being a unique entity and more about being one thread within a vast tapestry of equally valid experiences. Whether this is a profound insight into the nature of reality or an intolerable erosion of meaning remains an open question. What is certain is that quantum mechanics, through ideas like many worlds, continues to challenge not only our scientific models, but our most basic assumptions about selfhood, choice, and what it means to be real. Some scientists seek an even stranger explanation. An interpretation called quantum Bayesianism, or cubism, argues that quantum states do not describe objective reality at all. Instead, they represent the knowledge or beliefs of an observer about the system. Reality, in this view, isn't a fixed external thing, but a result of interactions between observer and observed. Before measurement, the universe exists as a cloud of possibilities, only becoming definite when interacted with. If cubism is correct, then the simple act of observing does not just reveal reality, it creates it. This raises the deepest, most unsettling question of all. If reality depends on observation, who or what was the very first observer that brought the universe into existence? If particles don't have definite states until measured, then what caused the first wave function collapse, the first definite event in cosmic history? Some propose that consciousness itself may be woven into the fabric of the universe. Others suggest measurement doesn't require awareness, but any interaction, such as a photon bouncing off a particle, may suffice to create reality. Still, this leaves the profound mystery of what existence looks like before measurement. Is it a realm of infinite potential, a superposition of all possible outcomes? And if so, is the reality we perceive merely one path through an immeasurable sea of possibilities? The double-slit experiment was just the beginning of the journey into this strange quantum realm. The deeper physicists probe, the more bizarre and haunting these questions become. Quantum mechanics is not merely a mathematical model, but a window into a world where the essence of existence is uncertain, where particles flicker between states of being and non-being, and where the act of observation might be the key that shapes reality itself. Yet despite its surreal implications, quantum mechanics remains one of the most thoroughly tested and successful theories in science. It powers modern technology, from computers and lasers to medical imaging, and continuously reveals truths about the universe far stranger than any fiction. Perhaps the most profound consequence of quantum theory is the challenge it poses to our understanding of ourselves. If the quantum world remains indeterminate until observed, what role do we, as conscious beings, play? Are we passive witnesses in a predetermined cosmos, or active participants shaping the fabric of reality? And since we are composed of these quantum particles, does uncertainty permeate our very existence? These are no longer just scientific inquiries. They are existential puzzles that quantum mechanics forces us to confront, fundamentally changing how we view reality, consciousness, and our place in the universe. Quantum mechanics has profoundly transformed our understanding of the universe, forcing us to reconsider the very fabric of reality itself. For centuries, classical physics depicted a world that was orderly and predictable, a place where objects existed in definite states, moving through space and time according to fixed laws. However, the advent of quantum mechanics revealed that this intuitive picture is only an approximation, one that breaks down when we examine the universe at its most fundamental level. In the quantum realm, matter behaves in ways that challenge our deepest assumptions about existence. Particles such as electrons, photons, and quarks do not possess fixed properties until they are observed or measured. Instead, they exist in a state of probability, a superposition of all possible states simultaneously. This means that before measurement, an electron doesn't have a single position or velocity. Rather, it exists as a cloud of probabilities encompassing multiple potential outcomes. Only upon observation does the particle appear to choose a definite state. This phenomenon, known as the measurement problem, unsettles the classical view of a deterministic and objective reality. This ghostly nature of matter implies that reality is not a solid, fixed construct, but something far more fluid and dynamic. The notion that particles exist in multiple states at once suggests that beneath the familiar world lies a sea of possibilities, an ever-changing landscape of potential realities. What we perceive as a definite outcome is, in fact, a collapse of this potential into a single, observed state. This challenges the very concept of an objective reality independent of observation. It raises deep philosophical questions. Is reality shaped by the act of observation? Is there an underlying reality that exists when no one is watching? Or is the universe itself a participatory process, where consciousness plays a fundamental role? Adding to this complexity is the phenomenon of quantum entanglement. Entangled particles become mysteriously linked, such that the state of one instantaneously influences the state of another, no matter how far apart they may be. This spooky action at a distance, as Einstein famously called it, defies the classical ideas of locality and causality. According to classical physics, no information or influence can travel faster than the speed of light, yet entangled particles exhibit correlations that appear instantaneous. This suggests that the fabric of space and time may be interconnected in ways that quantum mechanics is only beginning to reveal. Entanglement hints at a deeper, non-local layer of reality where separate objects are fundamentally connected, blurring the boundaries between them. The implications of these quantum phenomena extend beyond the behavior of tiny particles to challenge the very structure of space and time. Quantum mechanics suggests that space and time are not fixed backgrounds on which events unfold, but emergent properties arising from more fundamental quantum processes. The universe, in this light, is not a static stage, but a dynamic network of interactions, probabilities, and connections. Time itself may not flow in a simple, linear fashion as classical physics assumes. Instead, it might be flexible, with past, present, and future interwoven in a complex, multidimensional tapestry. This fluidity of time and reality opens the door to astonishing possibilities. For example, the concept of superposition implies that quantum systems can exist in multiple states or locations at once, raising questions about the nature of identity and existence. Is it possible that multiple versions of reality coexist simultaneously, each representing different outcomes or choices? Some interpretations of quantum mechanics, such as the many worlds interpretation, propose precisely this: a vast multiverse in which every possible event occurs in its own branch of reality. This view transforms our understanding of fate, free will, and the meaning of choice, suggesting that all possible futures are realized somewhere in an infinite cosmos. Moreover, the probabilistic nature of quantum mechanics undermines the classical idea of determinism. in the Newtonian worldview, given complete knowledge of initial conditions and laws, the future could be predicted with absolute certainty. Quantum mechanics, by contrast, introduces inherent uncertainty and randomness at the fundamental level. This is not due to ignorance or lack of data, but is an intrinsic feature of how nature operates. The famous Heisenberg uncertainty principle encapsulates this idea, stating that certain pairs of properties, such as position and momentum, cannot be simultaneously known to arbitrary precision. This intrinsic fuzziness means that certainty in prediction is limited, and the universe is at its core unpredictable in the way classical physics never anticipated. The unsettling, ghostly quality of quantum reality also affects our understanding of what it means to be an observer. Since measurement plays a crucial role in defining the state of a quantum system, the observer is no longer a passive witness, but an active participant. The observer effect implies that the act of observation influences the outcome of quantum events. This has led some physicists and philosophers to speculate that consciousness itself might be entangled with the fundamental processes of the universe. While this idea remains speculative and controversial, it raises profound questions about the relationship between mind and matter. Is consciousness a product of quantum processes? Could the universe be in some way conscious or participatory, with observers helping to shape reality itself? Quantum mechanics also reveals a universe rich with paradoxes that defy common sense. Particles can tunnel through barriers they shouldn't be able to cross, effectively passing through walls in violation of classical expectations. This phenomenon, known as quantum tunneling, has practical applications in modern technology, but also symbolizes the deep strangeness of quantum reality. Similarly, phenomena like quantum teleportation and entanglement swapping hint at ways information can be transmitted and correlated without traversing classical space-time pathways. These quantum peculiarities suggest that the universe is far stranger and more mysterious than previously imagined. The classical vision of a predictable mechanistic cosmos governed by absolute laws has given way to a picture of a reality that is probabilistic, interconnected, and fundamentally uncertain. This quantum universe challenges not only physics, but also philosophy, metaphysics, and our sense of place in the cosmos. The profound insights of quantum mechanics have also inspired new fields of research, such as quantum information theory, quantum computing, and quantum cryptography. These emerging disciplines leverage the unique properties of quantum systems, superposition, entanglement, and coherence to perform tasks impossible for classical systems. Quantum computers, for example, aim to solve problems exponentially faster than classical computers by exploiting the parallelism inherent in superposition and entanglement. These technological advances underscore the practical and theoretical importance of understanding the quantum world. Quantum mechanics compels us to rethink reality at its most fundamental level. It reveals a universe where matter is not fixed but ghostly and probabilistic, where particles are linked across vast distances in ways that defy classical space and time, and where reality itself is a fluid sea of potentialities rather than a static, predetermined stage. This quantum realm challenges our deepest intuitions and invites us to explore a cosmos that is far more interconnected, mysterious, and alive than ever imagined. The implications stretch beyond physics, touching on the nature of consciousness, free will, and existence, opening new horizons for science, philosophy, and human understanding. These ghosts of atoms permeate everything around us, and as scientists continue to probe deeper into the fabric of quantum mechanics, they are forced to confront an unsettling truth. The world we perceive, the reality we take for granted, is merely a shadow cast by something far stranger and more elusive. The deeper we peer into this quantum domain, the more it defies expectation and logic. Particles don't behave like tiny billiard balls in fixed positions. Instead, they seem to exist in multiple places simultaneously, a state that challenges our classical understanding of existence. Reality itself appears to shift and change, depending on whether or not it is being observed. But perhaps no discovery in quantum physics is as bewildering and as haunting as the phenomenon of quantum entanglement. Quantum entanglement is a puzzle so strange that even Albert Einstein, one of the greatest physicists of all time, could not accept it. Entanglement occurs when two or more particles become so deeply linked that the state of one instantaneously influences the state of the other, no matter how vast the distance between them. Once entangled, these particles remain connected in a way that transcends space and time. A change to one particle instantly affects its partner, as if some invisible thread binds them together. This spooky action at a distance, as Einstein famously called it, seemed impossible, violating everything physics had long held sacred. Einstein believed the theory was incomplete and that some hidden variables must be at work behind the scenes, some mysterious force that preserved locality and causality. Yet experiment after experiment, from the groundbreaking work of Alain Aspect in the 1980s to more recent tests, has conclusively shown that entanglement is real. The connection between entangled particles is instantaneous, defying the speed of light limit set by relativity. This revelation shakes the very foundations of how we conceive reality. Some physicists interpret entanglement as evidence that space itself is an illusion, suggesting that what we perceive as separate particles existing in distinct locations are in fact part of a single, indivisible whole. Others speculate that entanglement hints at hidden dimensions or unseen layers of the universe, where information can bypass the familiar constraints of space and time. Perhaps the most profound implication is the idea that the universe at its deepest level is not a collection of separate objects, but a vast, interconnected web where every particle is linked to every other. If this is true, then the boundaries that divide objects, people, and galaxies may not be fundamental after all. The cosmos could be one enormous entangled system, operating in ways we have yet to understand. But what does this mean for consciousness? Some researchers have ventured into highly speculative territory, wondering whether entanglement might play a role in the mysterious workings of the human mind. Could entangled particles within the brain connect thoughts and experiences across different regions, transcending the limits of classical neuroscience? Even more provocatively, might consciousness itself arise as a quantum effect, a phenomenon not confined to the brain but woven into the very fabric of reality? While such ideas remain controversial and unproven, they underscore how entanglement challenges our basic assumptions about the universe. It is no longer just an abstract concept confined to physics textbooks, but a fundamental property of nature that compels us to rethink the essence of existence. Entanglement is only one facet of quantum mechanics' profound weirdness. Another equally baffling aspect is the observer effect, the phenomenon whereby the mere act of observation alters the behavior of quantum systems. This effect was first famously demonstrated in the double-slit experiment, where particles such as electrons behave like waves when unobserved, but revert to particle-like behavior when measured. Soon, physicists realized that this effect was universal across quantum systems. At the smallest scales, reality itself refuses to take a definite form until it is observed. Particles exist as a superposition, a cloud of probabilities representing every possible state simultaneously. Only upon measurement does this superposition collapse into one concrete outcome. This challenges our intuitive notion of reality as something fixed and objective, suggesting instead that the universe is fluid and shaped by perception itself. If this is the case, what does it imply about the cosmos? Does the universe exist in a definite state when no one is looking? If particles and atoms do not possess fixed properties until observed, then might the entire universe be waiting to be seen into existence? Some physicists speculate that this necessitates a cosmic observer, a universal consciousness or intelligence responsible for collapsing wave functions and thus giving reality its form. This idea touches on profound philosophical and metaphysical questions. Is consciousness an integral aspect of the universe? Did the cosmos require an observer to bring it into being? Others argue against invoking consciousness, proposing instead that measurement need not involve awareness at all. Any interaction, such as particles exchanging information with their environment, may be enough to produce definite outcomes. Nevertheless, the mystery remains. If particles only assume definite states when observed, what about events that occurred before conscious observers existed? For example, the light from distant stars, emitted billions of years ago, remains uncertain until measured. Does that mean the past itself is uncertain until observed? These staggering questions reveal that quantum mechanics forces us to confront a universe far stranger and less comprehensible than we imagined. It is not a stable mechanical world, but a shifting, unpredictable web of possibilities where observation, entanglement, and superposition govern the very essence of existence. No longer can we think of reality as a world made solely of objects and forces. Instead, it is a world of probabilities and ghostly presences, slipping through our grasp the more we try to pin it down. Among the strangest features of this quantum landscape is superposition, the idea that particles do not exist in a single state, but in multiple states simultaneously until measured. While this seems impossible in our everyday experience, where objects have definite positions and properties, in the quantum realm, an electron, for example, does not orbit its nucleus like a tiny planet on a fixed track. Rather, it exists as a probability wave spread across multiple locations simultaneously. This wave of probabilities, described mathematically by Schrödinger's equation, only resolves into a single state when observed. This is dramatically illustrated by Schrödinger's famous thought experiment. A cat in a sealed box with a vial of poison triggered by a quantum event. Until the box is opened and the cat observed, it is neither alive nor dead, but exists in a superposition of both states. This paradox exposes the deep absurdity and mystery of quantum mechanics when applied to the macroscopic world. If electrons and atoms exist in superposition, why don't we observe such strange behavior in everyday life? Why don't we see objects simultaneously in multiple places or states? The most widely accepted explanation is decoherence, the process by which interactions with the environment cause quantum states to rapidly collapse, masking quantum effects at macroscopic scales. But could superposition be hiding in plain sight? Some physicists speculate that it might apply not just to particles, but even to large objects, or even consciousness itself. Could human beings exist in multiple states simultaneously, branching into different realities just as electrons do? Could we be unknowingly navigating a multiverse of parallel worlds? This leads to the many worlds interpretation, first proposed by Hugh Everett in 1957. According to this idea, quantum events never truly collapse, but instead spawn countless new universes, one for each possible outcome. Every decision, every quantum fluctuation generates a new branch of reality. In one universe, you turned left, in another, right. Every possibility plays out somewhere, creating an infinite multiverse of alternate histories. If this is true, what determines the reality we personally experience? Some argue that consciousness is tied to a particular quantum branch, giving us the illusion of a single coherent timeline. Others propose that all possibilities exist simultaneously, and our perception simply moves through them like a needle tracing grooves on a record. This idea opens profound questions about identity. If countless versions of ourselves exist across infinite realities, what does it mean to be you? Are we singular beings, or just one thread in an immense cosmic tapestry? Quantum mechanics is not just a theoretical curiosity. It is experimentally verified and continues to expand our understanding of nature. In 2010, researchers at the University of California demonstrated that large molecules made of thousands of atoms could be placed in superposition. More recently, experiments have suggested that even living cells might exhibit quantum effects. These findings hint at a universe where quantum strangeness permeates all levels of existence, not just the microscopic realm. If so, then we are not merely passive observers of a fixed reality, but active participants in a cosmic dance of probabilities, drifting between infinite possibilities. This leads us to the most unsettling question of all. Who or what is the ultimate observer? Are we collapsing reality simply by measuring it? Or is there something beyond us, a cosmic intelligence or universal consciousness that observes everything into existence? The implications of quantum mechanics stretch far beyond science. They challenge the very nature of existence, the meaning of reality, and the role of consciousness in shaping the world. We set out to understand atoms, the supposed building blocks of reality, but instead uncovered a universe far stranger and more mysterious than we could have imagined. At the heart of quantum mechanics lies one of the most perplexing phenomena of all: quantum tunneling. This is the ability of particles to pass through barriers that, according to classical physics, should be impenetrable. It defies intuition, yet is fundamental to many processes in nature and technology alike. Quantum tunneling is one of the most astonishing and essential phenomena in the universe. Without it, stars wouldn't shine, life might never have emerged, and the cosmos as we know it simply wouldn't exist. In our everyday classical world, a barrier is an absolute, an obstacle that cannot be passed without sufficient energy or force. Imagine a ball rolling toward a wall. It will either bounce back or stop dead in its tracks. It cannot pass through the wall. That defies all logic. Yet, in the quantum realm, the rules are radically different and profoundly strange. Picture a lone electron approaching an energy barrier, an invisible wall that classical physics says it doesn't have the power to cross. By all accounts, it should be reflected back, unable to move forward. But when physicists examine these microscopic encounters, something inexplicable happens. The electron sometimes vanishes from one side of the barrier and appears on the other, as if it slipped right through an impenetrable wall. This is quantum tunneling, a phenomenon that defies classical intuition, yet is predicted with absolute certainty by quantum theory and confirmed repeatedly by experiment. How does this happen? The secret lies in the wave-like nature of quantum particles. Unlike classical objects that occupy fixed positions and follow definite paths, quantum particles exist as waves of probability, clouds of potential locations and energies described by a wave function. When the electron nears the barrier, part of this wave stretches through and beyond it, allowing for a small but non-zero chance that the particle will tunnel through and appear on the other side. It doesn't break through like a battering ram. Rather, it ceases to exist in one place and reappears elsewhere, effectively skipping over the obstacle entirely. Far from a mere curiosity, tunneling is vital for the universe. Deep within stars, nuclear fusion powers their incredible energy output. Hydrogen nuclei must fuse to form helium, releasing enormous energy in the process. Classical physics says this should be impossible because positively charged nuclei repel each other fiercely, demanding impossible temperatures to overcome. Yet fusion happens thanks to tunneling, which allows nuclei to bypass their mutual repulsion and merge even under conditions where classical energy rules forbid it. Without this quantum trick, stars would remain cold, lifeless spheres, and the universe would be a dark, frozen void, devoid of the light and warmth that sustains life. But tunneling's influence extends beyond the stars. It plays a subtle yet critical role in biology too. In photosynthesis, plants use quantum tunneling to transfer energy efficiently through their molecular structures, harnessing sunlight to fuel life. Even human DNA may rely on tunneling to enable protons to shift between molecules, potentially causing genetic mutations that drive evolution. This suggests life itself is intimately woven with quantum laws, reliant on invisible processes that elude our everyday senses. Yet tunneling also raises profound and unsettling questions. If particles can bypass solid barriers, what does that say about the nature of space itself? If an electron can vanish here and reappear there, then what truly separates one location from another?
Some physicists speculate tunneling reveals a deeper, hidden reality beneath the surface, where space is not a smooth continuum, but a network of discrete points, and particles don't travel in a classical sense, but jump between these points.
This idea leads to even stranger possibilities. If quantum tunneling lets particles pass through space, could it also allow them to move through time? The connection between quantum mechanics and time travel has long intrigued scientists. Some interpretations propose particles might tunnel not only through physical barriers, but temporal ones as well, allowing them to influence past events or borrow energy from the future in ways that appear to violate normal cause and effect. This notion, called retrocausality, remains controversial, yet it invites us to reconsider time itself. What if time, like space, is just another barrier that quantum mechanics can circumvent? One of the most mind-bending theories comes from the Feynman-Steckelberg interpretation, which views antimatter as matter traveling backward through time. Positrons, the antimatter counterparts to electrons, could be electrons moving in reverse along the time dimension. If true, every interaction of matter and antimatter might be a fleeting moment where time flows backward. Even more enigmatic is Wheeler and Feynman's absorber theory, which suggests photons don't simply travel forward from source to detector. Instead, they involve interactions influenced by both past and future events, implying that quantum phenomena may be shaped by signals traveling backward in time. If this is the case, quantum mechanics might allow time loops, where future actions affect past outcomes, creating paradoxes that challenge our classical understanding of cause and effect. If time can be navigated like space, flowing forward, backward, or perhaps existing simultaneously, then our everyday experience of a linear past, present, and future might be an illusion. Quantum systems seem to exist in superpositions of multiple possible histories until observed, collapsing into one definite reality. The delayed choice experiment exemplifies this strangeness. It builds on the famous double-slit experiment, where a photon can act like a wave passing through both slits at once, or like a particle passing through just one slit, depending on whether it's observed. The delayed choice twist asks, what if the decision to observe the photon is made after it passes the slits? Astonishingly, experiments show the photon's behavior changes retroactively based on that future choice, as if the future measurement rewrites the past event itself. This defies all intuition. How can a choice made now alter what has already happened? It suggests the past is not fixed, but a fluid field of probabilities, waiting to be determined by future observations. Physicists debate whether this reflects a deeper, more flexible reality where time's arrow is not absolute, or if it's a quirk of quantum measurement. Some speculate that these quantum effects extend beyond particles, hinting at natural time loops and retrocausal influences in the macroscopic world. Could our own experiences of déjà vu, premonitions, or strange intuitions be subtle glimpses into a reality where past and future intertwine? If so, the implications are staggering. Time may not be the unyielding flow we perceive, but a malleable dimension intertwined with the fabric of existence, and perhaps with consciousness itself. In this perspective, the brain is not the origin of consciousness, but rather a receiver, much like a radio picks up signals. When the brain ceases to function, the signal of consciousness doesn't simply vanish, it detaches from the physical structure that once processed it. If this view is correct, then the mind is not merely a biological phenomenon, but a fundamental property of the universe itself. Some researchers point to quantum entanglement as a possible mechanism for how consciousness might transcend the physical brain. Entanglement is a mysterious connection where two particles remain linked no matter how far apart they are. If thoughts, emotions, and perceptions are connected through a deeper quantum network, then consciousness could theoretically extend beyond the individual mind, linking all living beings in ways we have yet to comprehend. Could this explain phenomena like telepathy, the claimed ability to sense another person's thoughts or feelings without any physical interaction? While mainstream science largely dismisses telepathy as pseudoscience, quantum mechanics shows that non-local connections, links that defy traditional notions of space and time, are not only possible but may be fundamental to reality's fabric. The observer effect, one of quantum mechanics' most famous mysteries, raises profound questions about consciousness's role. If simply observing a particle collapses its wave function, forcing it to take on a definite state, what role does human consciousness play in shaping the universe? Is it possible that the mind does not merely perceive reality, but actually creates it? Some interpretations of quantum mechanics suggest the universe does not exist in a definite state until observed. This idea is deeply unsettling. It implies that the cosmos is, in a sense, waiting for a conscious observer to bring it into being. If consciousness is essential to collapsing reality into existence, then who or what was the first observer? This question is central to a speculative concept called the participatory universe, proposed by physicist John Archibald Wheeler. According to Wheeler, reality isn't a static stage on which events unfold. It is an ongoing participatory process shaped by observation and interaction. This raises a tantalizing possibility. If the universe is shaped by observation, could the collective consciousness of all living beings influence the course of reality itself? And if the human mind is intertwined with the quantum fabric of the cosmos, could this explain some of the strangest, most unexplained experiences in human history? Take déjà vu, the eerie sensation of having lived a moment before, of experiencing an event that feels uncannily familiar. Could déjà vu be a quantum effect? Some researchers speculate that if consciousness exists in a quantum state, déjà vu might result from briefly crossing into an alternate reality, a glimpse of another version of events before the brain settles into a single timeline. Similarly, synchronicity, the meaningful coincidences that seem too unlikely to be random, has been explored through the lens of quantum mechanics. Theories propose that if consciousness interacts with the quantum field, then thoughts, emotions, and intentions might subtly influence reality, producing coincidences that are actually patterns woven into the quantum fabric of existence. Even dreams take on new significance under this framework. Some scientists suggest that during sleep, the brain may enter a state more susceptible to quantum influences, allowing connections across time, space, or even alternate realities. Could dreams be more than mental processing? Could they be fleeting glimpses into a larger quantum mind? If any of these ideas hold true, reality is not merely a physical construct. It is a deeply interconnected, participatory system. Consciousness is not isolated inside our skulls, but a quantum force woven into the cosmos's very structure. This leads us to one final unsettling question. If consciousness is a quantum field, what happens to it when the body dies? Some physicists propose that the quantum nature of consciousness allows it to survive bodily death, much like energy cannot be destroyed but only transformed. Could awareness persist beyond physical existence, continuing to exist within the quantum realm long after the body has decayed? Certain theories suggest that at death, the quantum information stored in the brain is released back into the universe. Individual awareness doesn't vanish. It dissolves into the greater whole, merging with the larger quantum field. If so, death is not the end of consciousness, but merely a transition, a return to the fundamental state from which all awareness emerges. This doesn't necessarily mean that personal identity is preserved. It may not be you as you currently experience yourself, but rather a continuation of awareness, an absorption into the vast quantum reality. If this is the case, what does it mean for the nature of existence? If the mind is not simply the product of the brain, but something far more fundamental, what role does it play in shaping the universe? Are we just observers watching events unfold, or are we something more? Could consciousness itself be the fundamental force that brings reality into being? Though these questions remain unanswered, one thing is clear. Quantum mechanics forces us to confront a universe far stranger and more mysterious than we ever imagined. The mind is not just a machine. It is a window into something far deeper, standing at the very edge of mystery. Beyond the limits of space and time, we may one day uncover the true nature of consciousness, what it means to be alive, to exist at all. If consciousness is not merely an emergent property of the brain, but something fundamentally linked to the quantum structure of the universe, then reality is far more complex and profoundly more unsettling than we ever imagined. The mind may not be confined to the body or isolated within individual brains. Instead, it could be something far more fundamental, woven into the very fabric of existence itself. This raises profound questions about the nature of self and the boundaries of personal identity. If quantum mechanics tells us that particles can exist in superposition and remain entangled across vast distances, could those same principles apply to consciousness? Might our thoughts and awareness connect to a larger quantum field, one that extends beyond our individual experience? Some scientists and philosophers have speculated that this could explain collective consciousness, the curious phenomenon where groups of people seem to share thoughts, emotions, or instincts across time and space. From ancient spiritual traditions, speaking of a universal mind, to modern studies on social intuition, evidence suggests consciousness may not be as isolated as we assume. Consider the enigmatic 100th monkey effect. In the 1950s, researchers observed Japanese macaques learning to wash sweet potatoes. Once a critical mass adopted this new behavior, monkeys on distant islands without direct contact began displaying it too. While skeptics argue this can be explained by indirect learning or environmental factors, some propose a radical idea. Once a new idea reaches a certain threshold, it becomes accessible to the entire species, as if awareness itself were stored in a shared cognitive space. Could this hint at a quantum field of consciousness, where information transmits not through physical means, but through an underlying entangled reality? Similar questions arise with savant syndrome, where individuals exhibit extraordinary abilities, photographic memory, complex calculations, instant mastery of art, without formal training. Some researchers suggest savants might access deeper layers of the mind, tapping into a quantum reservoir of information beyond individual experience. If so, personal intelligence may not be strictly individual. The brain could act as a quantum receiver, tuning into information stored non-locally, just as entangled particles share information instantaneously across distances. This idea resonates with ancient concepts like the Akashic Records, a cosmic archive of all thoughts, actions, and events. Could these mystical notions have a counterpart in quantum consciousness? If consciousness is indeed a quantum phenomenon, it forces us to rethink time itself. Could memories, thoughts, and perceptions be linked not only across space but across time? Some quantum physicists propose retrocausality, the future influencing the past, might play a role in human cognition. If the quantum mind transcends classical time, could some thoughts or instincts be signals from the future? This could explain precognition, the eerie sensation of sensing events before they happen. While skeptics dismiss these experiences as coincidences or subconscious pattern recognition, quantum effects might make precognition more plausible. If information can flow backward through time at the quantum level, then some thoughts, dreams, or intuitions could be glimpses of events yet to unfold. Such a view paints reality not as a strict march from past to future, but as an interactive, multidimensional field where consciousness helps shape the unfolding of events. And this leads us to a deeper question. If consciousness is not confined to the body, where does it go after death? Most scientists hold that consciousness depends entirely on the physical brain, and when the brain dies, the mind ceases. But if consciousness arises from quantum processes, if it is a fundamental feature of reality, might it persist beyond physical death? This idea, long central to religious and spiritual traditions, is now gaining serious attention among some physicists. The quantum soul theory proposes consciousness is stored at the quantum level in brain microtubules. When the body dies, this quantum information is not destroyed. It is released back into the universe, dispersing into the greater quantum field. This doesn't guarantee personal identity survives, but suggests awareness does not simply vanish. Instead, it returns to the source, merging with the fundamental fabric of existence. Such a notion aligns with near-death experiences, where individuals report feelings of unity with the cosmos, as if absorbed into a greater whole. If consciousness is quantum in nature, these experiences may not be hallucinations, but real glimpses into what occurs when the individual mind dissolves into the larger quantum reality. If consciousness exists outside of time and space, could life itself be part of an ongoing, never-ending process? Could reincarnation, the idea that consciousness moves between bodies across lifetimes, have a scientific basis? Some propose that since quantum information is never truly lost, individual awareness might, under certain conditions, be reintegrated into new forms. This may not preserve memories, but could allow the essence of awareness to be reborn. If consciousness transcends the human brain, then could the universe itself be conscious? Panpsychism suggests consciousness is not an emergent property of complexity, but a fundamental aspect of all reality, embedded in every atom, every particle, every structure. If true, the universe is not a cold, lifeless machine. It is alive, aware, and we, as conscious beings, are expressions of its own awareness, fragments of a vast, interconnected whole. If quantum consciousness is real, the mind is not just an observer of reality, it is a participant in its creation. It shapes the world just as much as it is shaped by it. And if that is true, then what does it mean to exist? Are we simply individuals confined by our thoughts and experiences, or are we something more, something infinite stretching beyond time, space, and the limits of our understanding? Reality is not what it seems. For centuries, humanity believed in a universe governed by certainty, a world of solid objects, predictable motion, and absolute laws. But quantum mechanics shattered that illusion. It revealed a universe built not from rigid particles, but from waves of probability, entangled connections, and forces that defy logic. At its core, quantum physics tells us existence is not fixed. Particles can be in multiple places at once. Time may not flow in a single direction. Reality is shaped by observation, collapsing into states depending on measurement. And perhaps most unsettling, consciousness may not be an isolated phenomenon trapped inside the brain. It may be woven into the very structure of the cosmos. The deeper we delve, the stranger the questions become. If quantum tunneling lets particles pass through barriers, could it one day allow objects or even people to do the same? If time loops exist at the quantum level, could causality be more flexible than we imagined? If particles remain connected across vast distances through entanglement, what does that say about the true nature of space? And if consciousness is tied to quantum mechanics, does that mean our awareness is part of a larger interconnected system? Could the mind exist beyond the body, interacting with reality in ways we have yet to understand? Every answer in quantum mechanics leads to new mysteries, deeper layers of strangeness. The universe we thought we knew is not a predictable machine ticking through time. It is fluid, alive, a vast network of energy and probabilities where observation fundamentally shapes what is real. And this brings us to the most haunting question of all. If reality is not fixed until observed, then who or what observed the first moment of time? Does the universe require an observer to exist? If so, what observed the first particle, the first event, the first cosmic fluctuation? Could consciousness itself be fundamental? Something not arising within the universe, but giving rise to it? Some interpretations of quantum mechanics suggest reality is participatory. Measurement is not passive, but creative. We are not just watching the universe unfold, we are actively shaping it through our perceptions, choices, and awareness. If this is true, then what does it mean to be alive? Are we merely complex arrangements of atoms following blind laws of physics, or something more, deeply entangled with the fabric of existence itself? The truth is, we do not yet know. But one thing is certain: the world we see is only a fraction of what truly exists. Our experienced reality is built upon forces we barely understand, and the nature of consciousness may be far greater and far stranger than we ever dared imagine. Quantum mechanics has forced us to confront the limits of our knowledge. It has shown us that the solid, predictable world is an illusion, and beneath its surface lies a realm where the impossible becomes possible, where matter is ghostly, where time and space dissolve into hidden structures. And as we continue exploring these mysteries, we arrive at a profound realization. We are not just observers of the universe, we are part of its deepest mystery. And in the end, the greatest question may not be what is reality, but who or what is experiencing it. Thank you for joining us on this extraordinary journey through the universe on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us where we unravel the darkest mysteries of space.